Madison College building construction for the fire service, homework problem, week 5, homework problem 4. This problem is going to incorporate a new element that you haven't seen before in these, and that is that we're going to have some number of real forces in the x direction. So we know that the sum of all of the forces in the x direction has to be 0, but for all of the problems you've encountered so far, you've not needed to calculate any. And for this one, you will see some x forces developed. Now, read the problem carefully. This is a bracket of some sort that has a pivot at point A, a rigid column or a rigid bar from A to B, and then a wire rope from B to C. It's loaded with a 500-pound load out here at the tip, but the beam itself, that beam from A to B, has a uniformly distributed weight of 100 pounds, right? So if we thought about vectors, there'd be a whole field of vectors all along the length of this thing representing a uniformly distributed weight. But remember that when we have a component like this of uniform section and uniformly distributed weight, we can consider all of that weight to act at the center as a single vector. So this is a weight of negative 100, and again, by convention, we would call this load negative 500 because it's in the downward direction. Now, the way to solve this problem, you actually have to start with the moments about point A. And I should say there are probably a number of different approaches to solving this, but the most expedient approach, because point A is a pivot, is to treat it, to use it as the point around which the moments are developed. So the sum of the moments about point A, well, what do they equal? Well, you have this 500-pound load that is 10 feet out from point A. So distance of 10 feet times negative 500 pounds. Plus, you have the moment created by this, the weight of the beam itself, which is effectively 100 pounds at a distance of 5 feet. So 5 feet times negative 100 pounds. And notice that both of these are producing a negative moment, which is going to want to produce a clockwise rotation. Now, there has to be some moment keeping this thing in static equilibrium, and that moment is created by the wire rope. So this wire rope is pulling upward and leftward at point B. But just like you saw in the vector practice, we can decompose that into a vertical component and a horizontal component. And what do we know about the horizontal component? Well, we know that the moment generated by this wire rope pulling up at point B has to be able to cancel out these other two. So we could think of this as, I'm going to say, I'm going to call it Fy at B. What does that say? It's the force in the y direction, it's the vertical force at point B times the distance from the fulcrum, which is 10 feet. And what do all of these need to add to? They all need to add to 0. Now you might be thinking, well, okay, you've accounted for this vertical force, but what about this horizontal force here, right? This is a component of the vector too, and it is. What allows us to ignore that for this at this point is the fact that it is axial to point A. That is to say that this force, this horizontal component, is pushing exactly straight through the center of the pivot. And when you're axial to the pivot, there is no distance, and so by definition, there is no moment. So for the moment, we don't need to consider that horizontal component. Now, let's push this formula around and see what we get. So 10 feet times 500, that's a negative 5,000 foot-pound moment, plus 5 feet times negative 100, that's a negative 500 foot-pound moment, plus the force at y times the distance of 10 feet, all have to add to 0. Well, let's take this stuff and push it over onto the other side. So negative 5,500. So if I add 5,500 foot-pounds to both sides, I get the force in the y direction at point B equal to, I'm sorry, it's actually 10 times the force because I still haven't done anything with that distance. 5,000 500 pounds. And then I just simply divide both sides by 10 feet. So the force in the y direction at point B, divide both sides by 10, and you get 550 pounds. So this vertical component, 550 pounds. Now, we've calculated at this point all of the forces in the y direction, so we can add them up. So let's look at the forces. The force in the x direction equals the negative 500-pound load that the sign is creating, the negative 100-pound load, which is the weight of the beam, the positive 550-pound reaction created by the wire rope, and some force in the y direction at point A. Right? This pivot, because this beam has some weight, has some component. So plus force in the y direction at A. What do all these have to add to? They all have to add to 0. So if we think about negative 600 plus 550 is negative 50 plus the force in the y direction at point A equals 0. If we add 50 to both sides, the force in the y direction at point A equals 50 pounds. And it's positive, which means that this pivot is pushing up on the end of the beam with 50 pounds force. And now we need to take a look at forces in the y direction and the tension in the wire rope. So now to work out the tension in the wire rope and the horizontal forces, we need to do an analysis of this triangle. And so this will be just a classic trigonometric vector analysis, and let's think about the things we know. We have a vertical component and a horizontal component that are by definition perpendicular. And we have a hypotenuse that's going to represent the length, the length of the hypotenuse is going to represent the tension in the wire rope. This included angle is 37 degrees, and we have already figured out that the vertical component that the wire rope is pulling is 550 pounds. So, what do we need to know? Well, we're trying to relate this tension in this hypotenuse to what we already know, which is the angle and the 550 pounds. I'm going to label this tension as T sub WR for tension in the wire rope. Well, now you need a trig function that relates the two things we know and the one thing we're trying to find. So if you think about the basic functions, so, ka, toa, we're looking for something that relates opposite, which we know, to hypotenuse, which we don't know. So opposite and hypotenuse, it's the sine function, and specifically sine of 37 degrees equals the opposite, which is 550 pounds, to the hypotenuse, which is the tension in the wire rope. Now, we're trying to get the tension in the wire rope by itself, so we're going to multiply both sides by that. And you get tension in the wire rope times the sine of 37 degrees equals 550 pounds. And now it's just simply a matter of dividing both sides by the sine of 37 degrees. So the tension in the wire rope equals 550 pounds divided by the sine of 37 degrees. And remember that the sine function is just a ratio, so there are no units associated with this. So you'll notice the only units that we have are pounds, which is good because we're going to measure the tension of the wire rope in pounds. Now, from a practical standpoint, it's probably easier to deal with the sine function first. So I'm going to say 37, I'm in degrees mode, I take the sine, and now I'm going to use the 1 over key and I'm going to multiply that by the 550. So if we take the reciprocal, we can multiply. Dividing by a number is the same as multiplying by its reciprocal. And I find that the tension in the wire rope is about 914 pounds, which agrees well with the answer given in the key. There may be some slight rounding differences, but that's pretty darn close. So we've figured out the force at AY, 50 pounds. We figured out the tension in the wire rope, 917 pounds. The last thing to think about is the Y force at point A. Well, this wire rope is pulling up and to the left, which means that point A has got to be pushing to the right with exactly the same amount of force as this wire rope is pulling to the left. So let's rethink about, now we're going to try and think about this force, this horizontal component, and I'm going to label this as compression in member AB. It reflects basically how much force point B is pushing towards point A as. Or, another way you could think of it is compression at in member AB is equal to the force in the x direction at point A. So now you need a function that's going to relate to this adjacent side to the opposite side. So if you look at the basic trigonometric functions, the tangent function is what relates opposite and adjacent. So we can write tangent 37 degrees equals opposite over adjacent. So 550 over the compression in member AB. Now we multiply both sides by the compression in member AB is times the tangent of 37 degrees equals 550 pounds. And again, we're trying to get the compression in member AB by itself, so we got to divide both sides by the tangent to 37. So compression in member AB equals 550 pounds over the tangent of 37 degrees. So again, we'll start with the trigonometric function, so 37 degrees into the tangent, and we're going to take the 1 over, and we're going to use that to multiply now by 550. And we find that the force, the compression in member AB is approximately equal to 730 pounds. Well, that means that, if you were to cut this, the pieces would come together, or another way to think of it is that this member, this beam AB, is pushing to the left with a force of 730 pounds, which, again, agrees closely with the answer given in the answer key. Some perhaps slight differences in rounding, but that's how you resolve this type of problem. So the thing that was really operative in this problem was understanding that axially loaded members basically exert a force that is along their axis. Now, wire ropes can only be axial. You can't push a string. A wire rope will always exert its force over its axes. Columns may or may not be axially loaded. In the case of this column, the column from A to B, this beam here, that was axially loaded, right? All of the forces ran straight down the center of the beam. And when you see that axial loading, that's an efficient structure, because if we were to look at this this beam from A to B, if we were to look at it kind of in section, what you'd find is uniform compression over its entire height. So it acts different than a beam in a traditional sense that has compression on the top and tension on the bottom. This is uniformly in compression. And if we were to look at this wire rope in section, you'd find a similar thing. It is purely in tension over its entire cross section. It's equally tensed. What that means is you're getting the most out of the material. Now, this is a really simple structure here, but it's a good kind of preview of what you're going to see when we get into talking about trusses. And what makes a truss is the fact that all of the members are loaded purely axially, as this wire rope is and as this beam is in this structure. So it's an efficient way to carry loads.